Hello everyone. Once again I welcome you all to MSP lecture series on transcendental chemistry. This lecture is 32nd in the series. In the last few lectures we are discussing about the classification of ligands by donor atoms, and let us continue discussing on various ligands, and because ligands are integral part of coordination chemistry. If you understand the nature of coordination modes, the nature of the donor atom and how they can bind and what are the binding modes, it comes very handy later when we want to use them in some applications, especially in material science or in homogeneous catalysis or even in drug discovery or in biological studies. So, from that point of view, understanding systematically the nature of the ligands and their binding properties is very important. With this, let me continue from where I had stopped. In my previous lecture I had initiated discussion on synthesis of isocyanide complexes and the reactivity of bound isocyanide complexes. With few examples I showed you, one can make coupling products from cyano complexes, isocyanide complexes. At least in order to see coupling reactions happening, we have to have minimum of 2 isocyanides on a metal center, and in case if we have more, probably apart from 1 or 2 others will remain as terminal isocyanides, and depending upon what stoichiometry we are using, 2 or more set of isocyanide ligands can participate in coupling reactions. So, after completing the discussion on coupling reactions, let us look into electrophilic attack. So, usually electrophilic attack can give alkylidine complexes. Okay, let us start with one simple general example to make you familiar with this kind of electrophilic reactions that happens with bound isocyanide ligands. Just for understanding, I have taken only one CNR. It does not mean that it is a monoligated metal complex or something. Let us assume we have several other ligands on metal. Okay. And this intermediate species will be in equilibrium with So, this is the end product. You can see this is alkylidine moiety here. Let us take a specific example now to understand this reaction. Perhaps you know what is DPPE, 1,2-bis diphenyl phosphinoethane. So, bridging isocyanates have very high nucleophilicity and are readily attacked. For example, if you take a complex where isocyanide is acting as a bridging ligand, let us consider this example here. If you treat this one with methyl iodide, of course right here. So, with these examples let us move on to nucleophilic reactions. So, nucleophilic attacks either at carbon or at nitrogen, that can give alkylidene complexes, unlike electrophilic reactions where we got alkylidene complexes. When nucleophilic attack occurs at either carbon or at nitrogen, that leads to the formation of alkylidene complexes. Let us look into a few examples in this case. So, this moiety is referred to as alkylidene. So, that means if you have metal 2, this is alkylidene, and if you have metal 2 carbon triple bond, this is called alkylidene complex. It is like acetylene, alkyne and alkene type. Let us look into one more example here. When you treat this one with ethanol, this is another interesting example for the formation of alkylidene complex. So, unless otherwise no specification is given, when Cp is written, assume it is cyclopentadienyl ligand having hapticity of eta 5. So, in general one should remember, if nothing is mentioned about this one, and if something is shown, this indicates it is eta 5 C5 H5. Okay. So, iron is in +2 state, then this is treated with sodium borohydride. I have given 3 different type of examples to show how nucleophilic reaction occurs at either carbon or at nitrogen that leads to the formation of alkylidene complexes. With this I stop discussion on ligands having carbon as donor atom. Of course, as I mentioned, carbon monoxide is the most common ligand with respect to carbon donor atoms. And since you are all familiar with carbon monoxide, I did not discuss in an elaborated manner about those compounds. Nevertheless, we come across while discussing lot of other reactions, CO compounds or metal complexes having CO. Now, let me move on to nitrogen donor ligands. Nitrogen donor ligands are plenty. One can see the list here, it is never ending. The simplest but hard ligand with very weak sigma donor and very weak pi acceptor ability is dinitrogen, a neutral ligand. It can be a 2 electron donor or it can be 4 electron donor. and then ammonia, the most common classical ligand we come across, and then all primary amines, both alkyl and aryl, and also secondary amines and also tertiary amines. And of course, from NH3, if you eliminate one H, it leads to the formation of NH2 minus. This can also act as a ligand, or if you remove 2 hydrogen, then we get amide, and then if we remove all the hydrogen atoms, then we get nitride. All these are very good ligands, and numerous examples are known in each case. And when it comes to cyclic heterocycles, pyridyl ligands are very prominent. We have plenty of pyridyl ligands and also N macrocycles and also skiff bases. And apart from this, we also have EDTA, ethylene diamine tetraacetic acid, where we have 2 nitrogen atoms along with 4 carboxylate oxygens, and TMEDA, another very useful ligand, tetramethyl ethylene diamine, and ethylene diamine itself is an excellent bidentate ligand that forms very stable 5-membered rings. And also apart from ethylene diamine, we also have diamine, triamine, tetramine, and also polyamines. To make you familiar with nitrogen donor ligands, I have listed some important nitrogen heterocycles here. You can see lot of this can be a bidentate ligand, this can also a bidentate ligand, this triazole can be a tridentate ligand, and pyrrole can act as an anionic ligand. Besides acting as an anionic ligand, it can also act as a neutral ligand, 4 electron donor when it is N minus, and imidazole we have, and we have something like this imino system we have. And when it comes to bipyridines, we have 2,2-bipyridine, very useful for chelating into a metal center, and this is very useful for bridging, especially this ligand is widely used in making metal organic frameworks. And then in photophysical studies, 1,10-phenolphthalein is very important, and terpyridine, and also 1,8-naphthyridine, purine, adenine, and also we have hexapyridine, taurine. Apart from those, we also have, of course, this one is ethylene derived phosphine. Here nitrogen can also act as a ligand. Many times when nitrogen is very close to phosphorus, because of the establishment of multiple bond between phosphorus and nitrogen, on most of the occasion nitrogen lone pair is not available for bonding. In this case, although nitrogen is trivalent, what happens, phosphorus is taking electrons from nitrogen lone pair to its sigma star. So, that we call it as negative hyperconjugation. In case of metal complexes, we call it as back bonding. Because of these things, whenever a nitrogen is next to phosphorus, it loses its donor abilities because its lone pair participates in binding with phosphorus. In some books they say it is d pi p pi interaction. It is not d pi p pi interaction, it is p pi sigma star interaction, that is called negative hyperconjugation. And of course, ethylene diamine tetraacetic acid, I told you, once this will always exist in the stable form having here zwitterionic form, and that is the reason if you look into the pKa, 3rd and 4th pKa values are very high because it is on NH and it is not so easily it can be deprotonated, and ACAC is there, and that is of course this is an oxygen donor ligand. And then we have porphyrin, the simplest porphyrin. I will show you at the end how to prepare this one. And another one is phthalocyanine. Phthalocyanine is prepared from this dicyano benzene, and one should remember that this can be prepared only in presence of a metal, so that this grows in surrounding the metal, that means it is an encapsulating ligand, and then it usually does not exist independently without metal ion. And of course, about these things I already mentioned in one of my previous lectures. So, now let us look into few ligands one at a time. Let us first look into dinitrogen. Again, dinitrogen chemistry is very important because we have plenty of that one in the atmosphere. One can make lot of useful nitrogen compounds as simple as ammonia. People always look for very mild conditions to make ammonia, unlike Haber's process that requires high temperature and high pressure. For that one, the better option is looking for ideal metal complexes. So, the first dinitrogen complex was made by Allen and Sinoff in 1965. They used this method of treating rhodium trichloride trihydrate with hydrazine to get this pentamine dinitrogen ruthenium dicationic complex. Of course, we have several methods I shall tell you later. First let us look into the possible coordination modes of dinitrogen. So, nitrogen, if you see here, this has 2 lone pairs are there here. So, these lone pairs can go to metal. So, it can act as a terminal ligand or it can also act as a bridging ligand where both the lone pairs on nitrogens are utilized, and of course, this is same as that one, and of course, you can also have 2 different metals, homo bimetallic system or hetero bimetallic system you can have, or this lone pair can go to 2 metals. So, you can have a trimetallic system, or we can cleave one of the bond in this fashion. We can also form some sort of immunotype compound here where we have this bent structure, or one can also see this kind of binding, or one can also see this kind of binding also once if we break 2 bonds between nitrogen atom. The end-on is when we have 1. So, eta 1 type is the most common mode. In most of the metal complexes we see this one, and whereas other lone pair remains intact. This is the most common one, this is called end-on, and this is also called as eta 1 mode. This is the most common one, and just if you look into free nitrogen, in free nitrogen the distance between N or Nn bond length is 1.097 angstrom units, whereas in case of nitrogen compound it is increases and it can range anywhere between 1.10 to 1.16. Most common bridging mode is linear, this is the one. So, that means you can assume that the triple bond is still intact, that indicates that the bridging nitrogen is linear and it is almost close to 180 degrees. In that case what happens, Nn distance will be around 1.1 to 1.36 angstrom units. So, now let us look into the synthesis of nitrogen complex. If I want to make for a specific application, how to make dinitrogen complexes in the laboratory. First one is a reduction method. Of course, reaction has to be carried out under positive pressure of nitrogen because we are inserting nitrogen. So, this is one of the method. Of course, here DEPE is bis diethyl phosphinoethane, very similar to DPPE. So, 1,2 bis diethyl phosphinoethane, and this is a chelating ligand. So, 2 chelating ligands are in this fashion and it is a square pyramidal molecule. So, one is using this reducing agent. You can do substitution reaction, that means replacing one neutral ligand with another one. For example, if we take treat this complex with N2 in methanol, it can just simply substitute hydrogen molecule to form dinitrogen complex. As I mentioned, DEPE is nothing but bis, you can see 1,2 bis diethyl phosphinoethane, and similarly This is also 1,2 bis dimethyl So, these two are widely used methods in the preparation of dinitrogen complexes. Of course, if you want to look into more, always you can go to advanced inorganic chemistry by F.A. Cotton and others. You can see lot of examples, and also you can see some literature that one can use, and also there are reviews are there about dinitrogen complexes, one can get more details. So, before I proceed to look into reactivity of coordinated nitrogen, let me show you some similarity between various other ligands. For example, when we see ligands such as isocyanate, carbon monoxide, dinitrogen or nitrosyl ligand, we can perform at least 2 type of reactions, if not 3. So, they are nucleophilic substitution reactions or nucleophilic or electrophilic reactions. That means how electrophilic reactions and nucleophilic reactions can be started in this. Let us look into some similarities. So, Mn2 can be conveniently written in this fashion. Okay. So, that means this one we can show in a format like this due to the movement of electrons. So, something like this. So, now the moment I write like this, delocalization of electrons, you should be able to know if where nucleophilic attack happens and where electrophilic attack happens. One should remember about this one. So, later when you are using electrophilic attack or performing nucleophilic attack, you should be able to tell where this nucleophile or electrophile are going to attack the bound ligands. This is very similar to what we come across in case of carbon monoxide. Carbon monoxide, if I take like this, to start with has a positive charge and it has negative charge, that means electron rich, and because now carbon monoxide is donated a pair of electrons to sigma bonding, as a result what happens, there will be net positive charge, and then depending upon how much back bonding occurs, next stage is something like this. Okay, almost we have ketonic and bond strength is weakening as far as CO is concerned, and then in the extreme case what happens, one can see something like this. This one. So, more and more electrons are donated from metal to pi star, and as a result what happens, metal to carbon bond strength increases and CO becomes weaker. And now if you consider this one, something like this, we can see here something like this. So, now we can see how nucleophilic attack happens, where electrophilic attack happens, and same strategy one can use to understand the reactivity of bound cyanide as well, isocyanide as well. Now you can see the similarities between some of these ligands. So, since similarities we are seeing, that is the reason we can see a variety of reactions that happens on bound one. So, in some cases coupling can happen readily, but invariably you can come across nucleophilic as well as electrophilic reactions. Let us look into more such reactions with bound nitrogen, that is very important from synthetic point of view. Until then, have an excellent time reading chemistry, especially coordination chemistry, and especially getting more information from textbooks about the ligands and their behavior when they are brought very close to the metal center.